At the CLE, we have a diverse group of researchers working on the legal and economic aspects of technology and policy, also collaborating with the ETH AI Center on regulatory issues and legal tech. A theme of today's conference is that a fair and effective policy for artificial intelligence will require contributions from government, from business, and from academia. And in the next section, we're going to be moving even more to the academia side. We will now have the first academic research spotlight with 3 presentations on cutting-edge research in AI and related policy issues from the ETH and EPFL. For each of these presentations, we will have some time for audience Q&A, and I ask that you put questions in the Zoom chat, and I can ask the speakers directly. So we have 3 presentations by Karl Aberer, Ryan Cotterell, and Carmela Troncoso, and I'll introduce them in turn before their presentations. But first, we'll start with Karl Aberer. Karl, so feel free to turn on your video so we'll get your slides going at the time. Hi, Karl.
Hello.
Great, the sound is working as well. Professor Karl Aberer is from the Distributed Information Systems Lab at EPFL. Today, he will present on social networks and trust in AI. Karl, the floor is yours.
Okay, so thanks for inviting me to present here a little bit of our work in the general context. So I've slightly changed the title, I've extended it. That's kind of an interplay between different dimensions: social networks, trust, AI, and science. And we have been working in these areas quite some while. I would like to highlight some of the things that we have done, and this might then give you some ideas what are implications in terms of policy, of legislation, but also understand probably some of the issues that occur in that space. So what I will focus on is essentially the way of how we are obtaining information, in particular news information today. And we have, in fact, if you like, in a slightly simplified way, we have 2 main channels that we have available today. The one is social media, which is based on user-generated content, but it's, by the way, also used a lot by the traditional media. And it's probably the channel that is being used predominantly by the younger generations. Now we all are aware of the problems that this comes with. On the one hand, there is a kind of weak or no quality control depending on the platforms. And this then has as a consequence that we will also find typically a lot of misinformation. And I think we are all aware of these problems as they have a lot of political and other implications. On the other hand, let's say the older generations like myself still are using traditional media to obtain news. And so when looking at the way of how these media obtain their information, there is, of course, still what we would call probably traditional journalism. This involves also the interaction with experts or the non-interaction with experts, which is particularly relevant, of course, as soon as we are looking into questions of scientific nature. What we should not oversee is that not only traditional media are feeding a lot social media, but the inverse is also true. They also draw a lot of information from the social media. But the other phenomena that you observe today is also that media are forming conglomerates, so also news is being shared across many different newspapers and media channels. And the new development is also that we have more and more data-driven journalism. Media, of course, they have one big problem. They have to survive in this attention economy, and we all know about problems with advertisements and so on. And this is, of course, also an impact of how news are being produced, how news are being disseminated. And finally, they also might be affected by misinformation, though we have, let's say, more trust that stronger controls of quality are in place. So what I want to talk about is different aspects of these ways of obtaining news. by looking at 3 case studies or 3, you can call it projects that we have been conducting recently. The first one, we'll be talking about how social news media can be used as an alternative scientific information source. In the second one, we look basically at the inverse direction of how news are being used to disseminate scientific information. And finally, we will look at a quite flagrant case of manipulation of social media, which then in turn again has also had some impacts on of how science has been performed. So we have in all of these 3 parts, we have some dimension of how science plays a role in news dissemination. First one I want to talk about is quite, let's say, a timely topic. So we are all now in the COVID crisis. There's a lot of discussion about vaccines, and particularly also about potential side effects, which has a lot of impact, of course, on the public discussion, the anti-vax movement, and so on. So now health organizations generally are, of course, interested to monitor exactly what is going on in this space, whether certain vaccines have certain side effects. And they have their very well-established traditional communication and reporting channels to obtain such information, which are typically very complete and based on expert knowledge. However, in some situations, these official channels have also some drawbacks. First, there can be significant delays. I know cases where it can take up to months since still an important piece of information arrives at the recipient. And there are also, so this is a temporary problem. There's also a spatial problem in the sense that there are regions in this world where these systems are not in place and where it's very hard to obtain any information. So that brings up the idea to have alternative ways of obtaining news related to side effects. And the obvious choice could be to monitor both news and social media for any kind of interesting information. And you see down there an example, which is a typical type of social media post that you could find someone saying or asking about the question whether there are problems with vaccination and menstruation. And so now this is, of course, not giving you any kind of proof of anything, but it could give hints that there might be an emerging problem which deserves further investigation. That's exactly what health organizations then would like to do. Now, the problem doing this is that, of course, we have in this media a lot of chit-chat, which has zero interest to this specific question, but it's not always easy to separate the interesting content from noise. So let me just illustrate this. So let's say you want to find reports on fatal cases of a COVID vaccine. And so you find here various kinds of reports. And if you would apply, let's say, a traditional way of information filtering, which would try to spot terms like vaccine or death, then you will find, of course, relevant content, but you will find also a lot of content which has nothing to do with a report on a specific case. So separating these different types of messages turns out to be a non-trivial task. Now, what comes to rescue, or what we could exploit in this context to deal with that problem, are recent AI-based language models. Technically, they're called deep transformer networks. And those have the capacity not only to understand or capture the meaning of isolated words, but they can really understand the meaning of whole sentences. Why is this so? Essentially, in a simplified way, they have been initially used for language translation, and for doing meaningful language translation, you cannot just translate word by word, but you have to really understand meaning of whole sentences. But in the meantime, we can use this for other tasks. And so using this technology, we can actually automatically determine that what you see here on the right side is actually not really reporting any specific case of a fatal case after vaccination, whereas the other ones indeed are such reports which are potentially of interest. So we deployed that in practice. We have been working with Linkalong, that is a startup of my lab, which has developed a platform for news and social media analysis. And so basically the bottom line is that without having these filtering capabilities, typical analyst would have to analyze just for one of these type of topics of interest, like fatal cases, hundreds of posts every day, which is a quite heavy burden because, of course, this is only one task among many. And what we could achieve is to reduce the volumes by more than a factor of 10, and this becomes quite manageable for such an analyst, and so enabled now a practical approach to monitoring this type of information. This is a nice example of how now modern AI can really help also to filter out basically noise in this huge information space where news are being shared. So second topic I wanted to talk about is now, so this is a bit in the other direction of how scientific information is actually disseminated in news media. And of course, I'm saying immediately also scientific misinformation. And again, we have now a period where a lot of such information is being found in media that related to the COVID crisis. So you see here just one example about a medicine which is called ivermectin. And so it is a very classical example of how a scientific study is misinterpreted in the media and then amplified through media, through social media. And even if later on things are put in perspective, the rumor continues to grow, and you see that it has really concrete consequences, like there are even administrations that recommend the use of this based basically on misinformation that has been spread. So the problem is, of course, that scientists produce results and journalists interpret them, and there's a lot of risk that this interpretation process fails, both, let's say, by misunderstanding, misinterpretation, but also by pre-made opinions, agendas, political agendas, but also economic agendas. So, for example, having journalistic products that attract a lot of attention motivates often to misrepresent some scientific information. So what we have been studying is of how can we counter such scientific misinformation. So if you look what is currently being used, so we have the gold standard, which is expert fact-checking. So there exist numerous platforms, some of them are shown here, where essentially experts read these articles and then they give their rating whether this is a credible piece of information or not. More recently, we see also that social media platforms provide users the possibility to provide some feedback whether they believe some information is false, which can then be used to further filter information. The interesting question is also, can we not also automate this process? So get away from purely manual, essentially, evaluation. And so this is what we have been studying, but not so much in the sense of, let's say, fully automating this evaluation process so that there is some AI that decides for us what is true and what is wrong, but rather to support humans in this process to make them much more efficient. And so basically it's a semi-automation process. Of course, when doing this, there's also risks, right? So if as soon as you have an automated process to determine truth, people will ask, why is the result coming up? So it's an interpretability question. Can we believe it? It's a trust problem. And if you run it, people might even believe that we do sort of automated censoring. So one has to be careful in this context. So what we basically pursued is the observation that for evaluating the kind of credibility of scientific reports in news, knowing about the context of these reports is absolutely essential. And so we can basically establish a hierarchy of the ways we can look at the problem. We can either look at it from the perspective of a specific claim. So that is, ivermectin is good against COVID. Or we can look at the perspective of an article that is talking about this claim. So there might be many articles doing that. And finally, about the sources that produce these articles. And at each of these levels, you can essentially establish context that helps you to evaluate the credibility of the information. So we addressed this from two levels. So for initially, we started to evaluate article credibility, and the idea was essentially to identify in articles many different features or indicators that could be used to assess the quality or the credibility of the article. And it turns out that depending on what kind of context information, be it the post in the social media, the content from the news, or a scientific publication, you have to apply very different methods to establish such features. In the second step, then, we rather concentrated on the question, actually, what we would really like to evaluate is not necessarily the credibility of a single article, but of a claim. So we started to analyze how can we establish the context for a claim in order to check whether it is kind of credible or not, which means we would not only analyze individual documents, but we would create a collection of related documents from news and scientific publications that would help then an evaluator to assess whether a claim is true. For doing all this, we have neat methods to generate context. That is where, of course, again, a lot of AI comes in. So we need vocabularies to collect the necessary content. You can use AI to generate and augment them. We use methods for entity extraction. So once we have text, we have to identify persons, scientific concepts in these texts. Again, this is something that's being used AI. Then language models like the transformer models that I have mentioned before to assess different characteristics of text. So for example, in a text, you would like to know whether it is a quote that says, okay, these scientists have been publishing a work saying this or that, or whether it is a claim like ivermectin is good against COVID and so on, or stance, or emotions and the perception that is communicated through the text. So for this, again, transformer models are very useful. And finally, using also knowledge graph to integrate background knowledge into the process of evaluation. All of this is quite complex, but it generates basically then this context. So here we see a screenshot of the first version of a system that we had that generates for an evaluator context that extracts different features at the article level. And we could show in experiments that this indeed helps to improve the quality evaluation. And for the evaluation of claims, I just would like to illustrate this by a case study that we did. So there is sometimes you find also contradictory claims in the news media. So you see here a claim about marijuana and post-traumatic stress order, and you find in two different journals essentially opposite statements. And so the system basically took these claims and then could identify a related article that is a scientific paper. So that was the automatic part in the process. And then we compared the evaluation of a non-expert that is provided this context with a non-expert that has this context. This we did using Amazon Mechanical Turk. The result is quite evident. Without the context, the non-experts essentially cannot decide the question. Whereas if they have such enhanced context, they basically come up with the same conclusions as an expert. And by the way, we have here also what other platforms for evaluating this type of claims have been producing. So Google Fact Checker could not find the claim essentially, and Claimbuster is a fully automated platform which came up with kind of a similar result, but was less certain about the wrong claims. So basically, this is ongoing work, but the main insight is that indeed with automated methods, we can improve the evaluation process by providing the contextual information. Now let me come to the third topic I wanted to address, and this is now the manipulation of social media, where we made some quite interesting discoveries lately, which is related to the creation of so-called grassroots movements in social media. So as you may be aware, in social media, often people self-organize around the topic or around some subject of interest, often a political one. They organize themselves, they organize then physical events and so on. And so these are the so-called grassroots movements. Now, some, let's say, malicious actors in this space see this also as an opportunity and try to create a kind of fake grassroots movements to attract attention in social media for many different purposes. And this activity is called astroturfing. So why is it called astroturfing? Because so you kind of build an artificial turf in the social media to simulate a grassroots movement. The techniques vary, so this can be trolls, so humans that kind of manipulate the discussions. It can be bots, so automated accounts. And as we figured out, in addition, it can also be by exploiting system vulnerabilities. So what exactly did we find? So if you go to Twitter, so you have typically the process, you have tweets, some of them are probably spam filtered by Twitter, but then the tweets that pass, they will be read and then they will be voted on. So voting that can be using the various feedback mechanisms that exist, either by putting the like button or by retweeting. So in this way, the tweet accumulates some attention, so some popularity within the social media platform. And if a tweet becomes very popular, then it starts to become visible in the so-called Twitter trends. And so if you're a user of a social media, these trends are basically then displaying some specific hashtags or other signals from these tweets that are considered to be very popular. And so basically then they will further amplify. Now, this is, of course, very practical to have a trend, because if the trend is in your sense, you can use that for advertisement, but you can also use it to pass on some political message. Now, in order to manipulate that, what we found is that you can also have bots that would produce some tweets, and then, since probably it's very unlikely that people will vote on these tweets coming from bots, rather, these operators, they use hacked accounts to create artificial voting. And now, this is, of course, a kind of a dangerous activity because you will leave traces. So, but what we discovered is that there is a mechanism where you can actually remove your votes after they have been issued. So basically, they remove the traces of pushing some specific message. And so the trend grows, but it leaves no traces, but the trend detection mechanism in the social media platform will still report that there is a trend. And so you have pushed this up to public visibility. And this is something that has basically not been known so far. And so just a quick question, how did we discover it? Or how could we analyze it? So the problem is, since this activity does not leave any traces, it's very hard to detect it in real time, because by definition, there is no trace. But what we could do is that we found that in the Internet Archive, you can get historical tweets, and there we find those deleted tweets. And so we could now identify trends that are faked. Well, how does this work? Essentially, we could identify the specific patterns bots are being using, because the tweets they post are kind of very nonsense-ish. And so then we just essentially search for similar tweets that have been deleted. And if there is a large fraction of deleted tweets, then we have found such a fake trend. And so this works actually surprisingly well, and the outcomes were kind of quite astonishing. First thing we found is that we identified more than 100,000 bot accounts, and to our knowledge, that's the biggest bot data set that has ever been reported in any single paper. We found about almost 20,000 fake trends that have been generated using this technique. And we found that actually what is really very astonishing is that these hacked accounts, in fact, have been in parallel being used by the bots and by the people without the people noticing that the bots use their accounts. So the accounts looked like legitimate accounts for a very long time. And the people didn't notice because of the deletion. They don't, basically, if you don't monitor continuously what's happening on your timeline, you will not notice that your account is abused. And the phenomenon, in fact, has been very popular in Turkey. We didn't find really any other country where it has been very widely used. But the interesting thing, almost half of the top trends in Turkey were were fake using this method. And they made even up 20% of the global top trends on Twitter. So this is in quite significant numbers. So what are some of the implications? The first is we found that, and here we are coming back to science, that scientists have been studying certain social phenomena in Turkey using Twitter. But basically, what they have been studying were these fake trends. So, and these were published papers in scientific journals. So really science has been deceived by this mechanism as well. We have then, I mean, the thing was also then reported in quite some media, but still up today, we have also reported this to Twitter, but they deny any responsibility, and still the trending algorithm is ignoring deletions and in that way enabling this type of manipulation. Okay, so that was it. These were the three cases. So basically, on the one hand, we have social media, news media is of course our source of information, but it's also our source of misinformation. I hope I've given you some examples also of how this impacts science. And as I could hopefully also convince you, we are using AI in many different formats. So it's not always, let's say, deep neural networks, which are very fashionable and very powerful today. Sometimes you use also some simple forms of AI and machine learning, and sometimes you use combinations. But these are really extremely helpful to basically do the basic task in any information analysis, separate signal from the noise and credible from the fake. And so that's all what I wanted to say. Probably just one final point to point out. So when we are thinking about the relationship between news and science, we often think about the dissemination of science in the media and then in the social media. But as you could see, there is also an impact of the media space onto science, sometimes in a very useful way, but sometimes also in a very dangerous one. Okay, so thank you for your attention. And if you have any questions, I'm happy to answer.
Thank you, Karl, for a very interesting and exciting presentation. I have a question in the time we have left before the next session. I was hoping you could comment for a second on the difference between detecting misinformation, which feels like what you've been focusing on, versus going to the next step of trying to regulate it or stop it or penalize it in some way. Are there any additional issues that you didn't cover there? Because it feels like the validity of information, it changes rapidly. Once you start penalizing misinformation, it changes the information environment, so it might be more difficult to keep the model working well. Do you have any thoughts on any unexpected issues with trying to use this misinformation detection for decision making?
So, I mean, as you may have noticed, of course, our focus is mostly on the detection part, because that is a classic, if you like, a classical information processing problem. When it comes into the reaction, I mean, we have fundamentally we have two ways, right? We have the technical means and we have the non-technical means, which are legal and regulatory approaches. So what concerns the technical means, I think that is essentially just a continuous arms race. Like if you think about bot detection, so initially bots have been, if you like, very stupid, and then it was not very hard to detect some typical patterns. Then these bots have been detected, and the bots became smarter, and so it's a continuous race. So whatever we have been doing 5 years ago on this field is probably in the meantime totally irrelevant. And so this is, I think, the general story that you have there. When it comes to regulation, I mean, you see the difficulties, right? Even a simple request to stop basically a mechanism that is obviously leading to misinformation already creates let's say some resistance, right? Or it doesn't receive a huge reaction. I think that's then at the end where really the regulators have to start to intervene.
Great, thank you, Karl. We will now go to the next presentation. We have Professor Ryan Cotterell from the Department of Computer Science at ETH Zurich. Ryan's research is in computational linguistics, natural language processing, and machine learning. And today, he will present on using AI to address social biases. Ryan, you should be able to share screen and now present.
Okay, can you guys see the...
We can.
Great. So I'm Ryan. I'm a professor at ETH, and I started about a year and a half ago. You can check out my group. which is called Ricola. It used to have a fun Ricola ripoff logo until some copyright folks told me that might get ETH in trouble. So now we have a generic Swiss background with blue that kind of looks like a lake and some mountains. But I think it's funny. Okay, so I'm going to talk a bit about gender bias in morphologically rich languages. This is a bit of a short presentation. And I have some more slides I could show if there's interest, or I could ask, or you could answer questions. Elliot's just did 10 to 15 minutes, and I think this will be roughly in that area. But of course, sometimes when you get into the groove, it goes a bit longer. Okay, though maybe less so in this in the Zoom environment where there's little feedback, but we'll see. Okay, so I'm going to talk a bit about gender bias in morphologically rich languages, as the title clearly suggests. And I'm going to talk a bit about what this is before I sort of go into concrete examples about my research. So people talk a lot about gender bias in machine learning, specifically gender bias in English. This is often left as an unspoken assumption. So many of us here are speakers of a language with some sort of gender marking on it, many European language. For instance, German marks gender. There are 3 genders, masculine, feminine, and neuter. Spanish marks 2. And we are talking a lot these days, or many societies are, about how to deal with the representation of gender in language. For instance, in German, there's a conversation about what they call the Gendersternchen. You can read about that all over the place these days. In Spanish, they have introduced a new declension class. So should have made a slide on this, but I think it's a cool fact. But in many sort of Spanish-speaking cultures within or societies or maybe communities within Spanish-speaking groups, they will use the word a as an ending. For instance, you might know that the Spanish word for friend is el amigo, and la amiga is the female friend, but many groups will start using le amigue to introduce a brand new class. So I'm not going to talk about sort of large level society issues. I'm mostly going to talk about machine learning, but this is sort of to set the stage for this idea that machine learning is a data-driven field. And in that sense, what our data are doing and how people interact with the data, specifically language data, is important. Okay. Are there any quick questions about that or any anecdotes before I start going into more of a concrete research project and the things I have been interested in? No questions. Great. Okay. So here's a picture that represents more or less a standard machine learning pipeline. We have that data goes in, feature extraction, we have a model, we make predictions. And this pipeline has largely remained unchanged for quite some time. What's in the middle has sort of changed. Maybe we have a deep neural network or we have this, but people have been, putting data in and getting predictions out for really 50 years, if not more. Of course, large-scale computing has made this easier to do, but the pipeline hasn't changed. And then we have a tech bro, which I'm going to represent by a Silicon Valley character. So there's a bit of a delay in how my my animations are rendering there. And this is sort of an attitude, which is sort of a caricature, but the data are the real world. So this isn't a machine learning problem. So this is sort of an idea that I think is sort of attractive to a lot of people, which is that, we don't want to touch the data because the data represent the world. And I'm going to talk for a bit about why this isn't really true. And also, even if it were true, maybe we shouldn't deal with it. But hopefully some of you have encountered this. It gets propagated in certain circles. Okay. So a simple example, which is not related to language or anything political, is what color is a banana? So does anyone want to guess what color a banana would be if you had to think of a prototypical banana? Do I have any interaction? Maybe Elliot? Oh, wow. Okay. We got someone who guessed it. Yeah, green. So the point here is that if you plot, if you search in Google Ngrams, what you're going to find is that green banana is more common than yellow banana. And the reason for this is because banana is assumed to be yellow. We rarely say yellow banana. In fact, if you say yellow banana, at least in English, I would have to say it in a context where someone expected the banana to be another color. So But this matters. And the reason why this matters is the fact if you're trying to extract a knowledge base or something from text, which many people in NLP are doing, or they're training, a large BERT style model on this text, it might learn that the banana is green. And how could it not? It doesn't have any other signal. It's not grounded in the world. It hasn't experienced a banana. So this is sort of a simple point, but it's to get across that, what's written on the internet isn't the world, even in some trivial examples. Hopefully I'll agree with that. Okay. I'm going to apologize for the lag. I think, great. So the problem here is sort of, as I said, humans don't talk about the world the way it is. Okay, so now let's talk a bit about gender bias in text. So this is sort of a bit more of a political issue, I think. I mean, and people have different opinions on it at times, which I'm going to try and avoid. I'm talking more about facts. So in the United States, the Department of Labor would say that about 50% of doctors are women. But Google Ngrams would say that's not really true. So this is sort of an interesting situation where society has retained a stereotype, even though it's not really true anymore. And I'm not really a sociologist. I'm not even a sociolinguist. I work on natural language processing and machine learning, but this is sort of basic, thinking about the data that goes into our models. And this is sort of changing, but at the end of the day, it hasn't really tapered off. So these are sorts of these, and when I talk about text, the reason I put in a sentence here is because when we talk about a bias in a natural language processing model, this is the origin of the bias. It comes from, disparate frequencies in sentences like this. Okay. Also, the data is also kind of bad, and so when I made these slides actually about a year ago, there was less attention to these issues in, say, machine learning. I think with the advent of GPT-3 and some of the discussion of what data they've been training on some of these models, this has been a point that's been brought up. Okay, was there a question? I see it was a hand gesture, which I'll interpret as positive. Okay, so back to the point of sort of the work I'm building up to, which is actually a single conference paper, but we have others, which is what to do in natural language processing for morphologically rich languages. So I'm going to use an example from Spanish. So Spanish has gender, very similar to German. Consider the words ingeniero and ingeniera, which mean engineer, female, and male. And the point here is that this also does not represent the world. There are biases in machine. I mean, there are disparities in engineering in terms of gender, but it isn't that bad. When we talk about the representation of women in engineering, it's depending on the field between 20 and 30%, among others. Again, these are rough statistics, but it isn't 1 in 100. So this really does not represent the world as we know it. And there's a couple of reasons for this. One reason is the fact that masculine is taken to be a default in these languages. And another, so that's almost a linguistic convention, sort of the example I sort of said before. Another example is simply bias, among other things. If you were to write fiction or write an article about engineer, maybe you default to the masculine because that's the prototype you have in your head. And also, even if this were the case, it would also really reinforce social biases. So to be clear where we're going, I'm going to get to a specific application. The reason this is a bit understudied is because a lot of people who research these topics focus on languages that look like English. They don't have endings, they don't have gender, and this turns very quickly into a technical problem. The set of tools I can bring to bear to mitigate this is very different depending on whether my language marks gender. A different set of mathematical tools will be necessary in the case of something like Spanish and German. Okay. And of course, it goes both ways. Spanish has a male and female version of nurse that are the same gender or same root, and you can see the same sort of thing there. So now we're going to talk about Turkish for a bit. So this is an interesting language. So Turkish is a language that does not mark grammatical gender. A lot of European languages don't mark grammatical gender either. Finnish and Hungarian are two examples. Estonian as well. It's very close to Finnish. So these are languages that have no distinction between he and she ever. You have to, and this is sort of an interesting point because a lot of people want to push English in this direction. And I've always found it interesting that a number of claims have been made that society would be equitable, but there are a large number of very non-equitable societies whose primary language do not mark German. Turkey would be an example. Perhaps a more extreme example would be Iran. Persian, standard Persian does not mark gender. Neither does Azeri, which is spoken, basically a dialect of Turkish, spoken very heavily in Iran. So many languages that sort of enforce rigid gender stereotypes don't actually mark gender in their language. So I think it's always important when talking about language to be careful about how much you think changing the language will actually change society. But that's just the general caution. Okay, so Turkish lacks grammatical gender. O means both he and she. For instance, if I say "U bir güzel profesör," that means he or she is a beautiful professor. And I can say "U bir akıllı profesör," which is he or she is an intelligent professor. So where you can go with this is that, well, if we have these sentences where there's no grammatical marking of gender, you might have a situation where someone could impose their own bias. So it's more of a controlled study. My text is no longer telling you what gender might be there. Okay. So I'm going to talk a bit about how we might come up with a test bed. So we input a Turkish sentence, and of course we're going to get out he is an intelligent professor. And that's completely due to bias in the model. There's nothing in the input that says that's what it should be. Okay, any questions about that?
Perfectly explained. I am an Azeri Turkish, that's why it's clear how you took the points here. And I really love that how you divide the context in these language roots. And I want to have one question: that do you think that it may be that Turkish people also doesn't make differences about like a third generation, let's say, who are the LGBT friendly? Do you think that it can be a good point?
So I don't. That's a very complicated question. The degree to which language affects thought is a very complicated and very controversial question. So I tend not to make public statements on that, or any research-related statements, except in very controlled situations. So I mean, a popular treatment of this would be the movie Arrival, if you've seen that. But I don't know to what degree this affects, our views of people, or could affect our views of people if we change it. There is certainly a feeling among some communities where gender is enforced in pronouns, like English speakers, that this will have an effect. And I just don't know much about the psycholinguistics behind it at all. And I don't think many people do, because it would be very hard to run a control study of a monolingual Turkish speaker and a monolingual English speaker. We'd have to have them grow up in the same society, right? It'd be very hard to affect a study that would give you evidence to that claim, if I understood your question. So I don't really know how speakers of a given language, how grammatical attributes would affect someone's view of minorities. And I think that's a complicated question. But yeah, thanks. It is a good question, though. I think it's interesting. I think speculation on that point is not inherently useful because it has been historically speculated about so much. Okay, so this means whenever we put in a sentence without a grammatical marking, we get back a gendered sentence, and this is purely based on bias in the model. Okay, so Google now has gender-specific translations for English. So this idea would be you can choose which gender you want, and this is sort of a nice sense in my idea. My sense of the world, the right way to do automatic translation, which is to say, identify a situation where the user has to make a choice and help them make it. So this is more of an HCI view of translation. There are other ways of thinking about it. You could imagine identifying cases where it's ambiguous, that is, context does not give away the gender. Larger context, and you flip a coin. There's different things you could do. So to sort of wrap up in the point that I think some of you will find interesting, is that there's a question about whether this works for German. So if we type in, Uber Güzel Doktor, that's he or she is a beautiful doctor, we'll get back, sie ist eine schöne Ärztin. With a suggestion that ist ein netter Arzt. So if you don't speak German, this is, she is a beautiful doctor, but he is a nice doctor. So it's actually picked up on different senses of the word Güzel, which is interesting. So basically there's no, Google has put in no, at least when I made these slides, it might have changed. They've put in nothing that sort of helps mitigate this problem in German. So this is sort of the state of the gender specific feature translation. And we can bring out the bias in the other way, where it'll say, he is a smart doctor, ist ein kluger Arzt, and there's no suggested translation. So this sort of turns into pretty quickly into a really interesting natural language processing problem, where we're going to try and build a model that's going to have to be quite sophisticated to allow us to sort of learn to manipulate the generated text. So that's sort of a problem I really like. It's very self-contained and it has applications. Okay, so the idea is that we're going to have a Turkish sentence with a gender-neutral pronoun. We're going to translate it. We're going to do a human intervention, and I mean intervention in the sense of a causal intervention, and then we're going to sort of re-inflect the sentence. And I didn't have time to go into the technical details, but there's a paper from 2019 on my website and subsequent work. I don't know all of that is published yet, that discusses how you build sort of machine learning model that would enable you to learn and manipulate sentences like this. Okay. One limitation is that we need to have sort of a list of words that are semantically equivalent, but those are pretty easy to scrape, at least for high resource sort of European languages. There's a question, is there still default if the user doesn't choose? I don't remember. You can check on Google Translate. I mean, there's two questions, what Google does and what Google ought to do. And those are often very different things. That's all I'll say about that. Okay, so I'll leave this slide up. That's sort of the end of the presentation. I have it clocked at about 18 minutes. So we were within the estimated time range. Are there any questions? Google Translate is adapting. They do that. So I should update the slides.
Well, thank you, Ryan, for the presentation. The Zoom chat is open for the next few minutes for questions. I had one to start the Q&A. Related to this question about language and attitudes, do you have any thought, if you survey people about the gender share for doctors or engineers, for example, is it going to be closer to the true shares in the population or to the language shares like you showed on Google Ngrams?
So that's a question I do know something about. So back in the day, when I was an undergraduate, I worked a lot in psycholinguistics laboratories. And one of the main manipulated variables in psycholinguistics experiments is based on gender. So what they'll do is they'll basically get they'll survey people and use norming studies to get how often we think doctor is a male or a female. And then they'll mismatch it with pronouns to get a delayed effect. And the point of these studies, the scientific background would be, they try and figure out whether the syntax license the delay. So you would only observe a delay and a mismatch if your grammar allows you to consider a certain link. So that's a bit high level, but that's a very common thing in psycholinguistics. So psycholinguists have been making use, and other branches of psychology have been making use of norming studies. And back in the 70s, you can find a lot of studies where doctor was very heavily biased, and it slowly has gone down. And actually, there's a movement now in linguistics to not use this variable at all. So I think this is well documented that these gender stereotypes are closing in certain cases, not all, in terms of perception. And it's also a function of the usual suspects: education background, age, geographic location. So, but yeah, we do have diachronic data on it, if that's something you're interested in. I would be, if you want to make a very precise statement, you might have to be careful to make sure the different studies were collected in similar ways, but that's always true of sort of psychological stuff. Does that answer your question?
It does, thank you. Are there any more questions? You can type it in the chat, or if you're able to unmute, please feel welcome to ask it aloud.
What would the recommendations be to acquire unbiased data in the future? I don't really know. So that's a complicated question. If you look at where NLP is heading, it's training very large language models on a lot of data. And this sort of research is almost exclusively practiced by large corporations that have A, access to the data, and B, access to the compute. I don't think they have a vested interest in removing bias from their data. And I don't think there's really a way of doing it easily, because you're talking about the entire web, I guess, that you'd have to remove. And these are sort of, what I've shown here is sort of simple examples, right? I mean, you can say something offensive or derogatory while using wonderful, clean words in a very subtle way. So I've often felt that removing bias from data, you know, at a non-trivial level, and I'm talking about a relatively trivial, superficial level at the syntax, would require a complete understanding of the sentence, right? Because what people talk about as bias is often subtle. It's like when people talk about microaggressions as, you know, people asking questions like, where are you really from? Like, what model is going to be able to pick that up as, you know, an offensive thing to ask someone who doesn't outwardly look like they belong in a community to some people, without understanding a whole lot of context. So I think you sort of have to come to terms with the data is always going to have some bias. It won't always go away, and you have to be very careful in what you deploy and where and why. Does that answer your question? Sorry, I guess it was a non-answer.
All right, thank you, Ryan. We'll now go to the next session in the Academic Research Spotlight. The third presentation is by Professor Carmela Troncoso. Welcome, Carmela. Carmela heads the Security and Privacy Engineering, or SPRING Lab, at EPFL, and today she will present on synthetic data anonymization Groundhog Day.
Thank you. Let me share my screen. So hopefully you're all seeing my screen now. And yeah, I want to talk a little bit about synthetic data and the promises that it makes. And we can actually talk at the end a little bit about how, I'm going to talk mostly about the privacy side, but how it also actually may not fulfill promises in terms of bias and that aspect. So synthetic data comes into play because people want data. This thing, we're here at the AI conference where the kind of bottom of everything is we want data. But we know that data, you know, sometimes you cannot use it because it has a lot of personal information, and then we enter in a lot of both legal and social problems about the fact that we cannot use this information in many ways. So back in the 2000s, people said, no worries, we're going to anonymize this data in such a way that, you know, it doesn't refer to any individual person, and then we're going to be fine. We're going to call whatever comes out of the anonymization mechanism a sanitized data set. It would allow the analyst to take statistical insights, and it should prevent privacy adversaries from coming back to any of the data that was here. But it was soon discovered that there is a trade-off between how much information do we allow for the analyst versus how much information we have for privacy adversaries. And in fact, if we kind of plot how things could be on how much privacy you have versus how much utility you have, the ideal case, we would like to have tons of privacy and tons of utility at the same time. But what has happened so far is that traditional sanitization techniques mostly fall on this side. They kind of have quite good utility, but they are also not very good at providing you with privacy. And if you kind of push them to improve privacy, what will happen is that you will end up in this quadrant here where you don't have utility. And here comes synthetic data and says, no worries, guys, we're going to solve this problem. So instead of an anonymization mechanism, we're going to put what we call a generative model that is going to learn from this raw data set how it looks like. It's going to learn the main characteristics of it. And then it will output a synthetic data set that It's not like sanitization makes a kind of a row by row operation on the raw data set. Here we would have something that, it's nothing to do with the real data set. So we really will enable all of the statistical insights, and indeed we will have these adversaries not being able. So they promised you the perfect trade-off. You're going to be able to do the same things that you could do with the main data, with the raw data, without any of the risks. So I thought it was fantastic, bit unbelievable. So we ran an evaluation, like a quantitative evaluation of whether this is true or not. And we wanted to know essentially, is synthetic data the real case, or is synthetic data somewhere here? Where does it lie, and what is actually, because the promise is that this should be here, but is this actually true? So first we went and evaluated the privacy gain, and the privacy gain is not really how much privacy you have from the synthetic data, but actually what is the reduction of privacy, or what is the improving privacy that you get when you do S synthetic instead of raw data R, right? We're interested in know how much you're gonna improve your privacy by doing this. Like we know that if it's sanitized data set, you're kind of on the low side, and in the ideal case, you would be here. Where does the synthetic data, how much does it help? And we had to define what privacy loss means, and to do this, we took kind of things that actually anonymization techniques were born to protect from, and things like what are called linkability attacks, where we can know whether a person was in a data set, like is the governor in the data set? The origin of this question is the seminal paper from Latanya Sweeney on anonymization, where she re-identified the governor of Massachusetts and then was able to find the governor disease in an anonymized data set. And the other thing that we worry about, the thing that we want to, is to actually prevent inferences. That's the main goal of making data anonymous or privacy preserving, that it does not allow to do inferences on the people in the data set. Like, what is the governor's attribute in the case of Latanya Sweeney? What was the disease he had? Why did he go to the doctor? So we went and evaluated a bunch of synthetic data mechanisms. We applied them to different data sets, and we checked it. And here's a graph where we show the privacy gain with respect to this linkability, with respect to this question, is the governor in the data set? The higher you are, the more privacy gain you have. So the more you gain because you transform the raw data into another thing. And we see that sanitization, like traditional sanitization, is respected. For some people, like if their rows are not very much modified by the algorithm, they have very little gain. Some of them have a lot of gain. This essentially means they were an outlier and the row got deleted, perfect privacy. And then here we have something called a BayNet, which is a synthetic data that is not thought for privacy. It's just to produce good synthetic data. And we see that it gives a bit more of a privacy gain, but it's not any wonder, right? This doesn't really go to this perfect thing of there is no privacy inference anymore. And here we have synthetic data that is actually thought to provide privacy protection. And for that, using differential privacy techniques, which is a tool that we have in privacy domain to ensure that the influence from inputs does not appear on the output. And to the right, we have those that are kind of configured to give more differential privacy. So that means we add more noise, and we see that the more noise we add, the more privacy gain we get. No surprise. If you don't add that much noise, then, it's not that you get perfect protection. But this is very promising, right? Because it seems here that we can actually get protection. We can get very good privacy gain. Now the question is, do we do this at what cost? Because at the end of the day, the goal of all of this is to produce data that is useful for the analyst. So we thought about, and we went and talked with a lot of people, practitioners, about what are the kind of things that you want to do with this data. And the first thing is some of them want to use the aggregate data, for instance, to train machine learning models. Like this is one of the things here in this AI conference we want to do. We would like to have data to train our models. And if we cannot touch the raw data because it's personal, give me something synthetic I can fit in my model. And then ideally, you would like that if you have a test accuracy in the raw data, you get very similar on the synthetic data. So we went and did that experiment in a couple of data sets. And here you have results like the accuracy that you get in the raw data. The dashed line is the baseline, random random prediction. And we see that if we sanitize the data, we get very similar utility. No surprise, we also didn't get much privacy. With Baynet, we get, we saw before that you get a bit better privacy, so you get a bit more of a loss in utility. And as we move to the right, to the places where we actually had privacy protection, we see how the utility plummets down. And when we really have protection, utility, sometimes even goes under the baseline, right? And this is the kind of thing that we see. It seems that privacy does not come for free. It's no free lunch. So this was first time we can see that maybe the promises of synthetic data are not so true. The other thing that people want to do with data is to create reports, to be able to publish statistics or to learn main trends in the data sets, right? I want to know the statistic of the raw data set, and I would like the statistics on the synthetic data to be the same. So we went and tested this, and with very normal statistics like the mean and the median of different columns in the data set. Here we had a data set that's called the adult data set. No, sorry, this was the Texas data set, which is about a hospital that has columns about the total charges paid by patient, the total charges paid on accommodation, or the total ancillary charges that patients have. And then we looked at, for each of these attributes, columns in the database, how good was synthetic data at allowing you to compute the mean. And here we see that sanitization and raw are very close, both for the median and the mean. But the moment that you start doing synthetic data, and here the one that doesn't have protection already has, this is 1 order of magnitude difference in the mean. But if you move to the right, you get up to several orders of magnitude and distance with the mean, which means that, if you want the statistics and you need to publish the statistics, you might as well publish the statistic of the raw data. You don't need to publish fine-grained data, just publish your statistics. And then this seems kind of, if you're just looking about these things, and it seems that a lot of this is a problem of these outliers, why don't you just remove the outliers? But when we talk with people that want to use synthetic data, we actually find out that one of the main use cases is actually outlier analysis. Like we talk with people in the financial sector that want to do fraud detection, and they need to keep these outliers because those are actually the frauds that are the kind of thing that they would like to classify. We talk with people on the medical domain, other field that is extremely interested on the potential of synthetic data. And in their investigations, a lot of the things that they do is actually finding these outliers. That's how you find rare disease and how you find the things that are going wrong, right? They're not really interested in the average population. You're interested in the things that go wrong. So we would like to know that the anomaly detection on the raw data is very similar to an anomaly detection in the synthetic data. And for this, we made an experiment in which what we did is to try to study how outliers influence other outliers, like how much having one outlier in the data set improves the prediction on other outliers. And here what we have, so for each outlier that we call ID1, ID2, ID3, we see, what is the amount of error that it induces on predicting other attributes. So when you have ID1, it turns out that the yellow one, which is ID3, gets a kind of it goes down in the prediction, but the green guy, the ID4, actually improves the prediction. So this is what happened with the raw data. And when we see it's like sanitization is kind of more or less similar. You have a bit worse influence, but it's still there. You have worse because some outliers are actually suppressed, right? But the moment that we move to synthetic data, what we see is that slowly, the influence of the outlier on others disappears. Effectively, it is also the case that these outliers are deleted, but instead of being deleted explicitly, as we do in sanitization, they get deleted in the feature space. So what we have here is that while we wanted to have this ideal case and we would promise the synthetic data would fall in this quadrant, you can have synthetic data that has almost as good utility as sanitized data, but at a very small privacy gain, or a strong privacy gain, but a very low utility, because either all your statistics are going to go off the roof, or you're essentially going to delete the outliers and you cannot really do the analysis that you were looking for. And why is this? Why is this suppression thing? So in sanitization, as I said, we do a lot of this suppression of information, delete outliers. like this kind of thing, like row by row, we look at them. And when something is kind of out of order, we just delete it because we know this is going to leak, it's going to be re-identifiable, and it's a problem. In synthetic data, when we do this extract features and then sample, this doesn't happen, right? It's not that there is a row by row correspondence between the raw data and the synthetic data that we can say you deleted. But what happens is that on the feature space, on the feature representation, there are actually these deletions. So what can happen, we can be in one of two cases. Imagine that we had this data set, and it can be that when we're doing our generative model, actually the model picks on this outlier, this 50-year-old man that tested negative for this disease in this database. And then what happens is that when we look at the statistics, because it's an outlier, we will see that in the age kind of there is a spike here. Would also appear one more test negative, one more gender male. And when we create our data set, it will actually look very similar to this one, right? And this will be great for the analyst that will know that female and male are equally likely to test positive, similar to what we had here. But it will also be very good for the attacker that now can really pinpoint kind of the signal of this outlier in this data set and can say, oh yeah, I know this, I had this male as my target, and now I know that there are in the data set, because otherwise we would not see this record here. It's a bit more complicated than that, but it's really like the influence of this outlier really shows on the output. On the second case, it can happen that the model actually does not pick on this outlier, as we said before, kind of deletes it. And then when collecting the statistics and when doing this, the synthetic data set, we don't have the representation. It is great for privacy, right? There's no more information about older males. There is nothing else we can learn about them. But also for the analyst, this will be disastrous, because now probably they actually guess that females are more likely to test positive than men, and you're just getting wrong conclusions. And what really makes synthetic data a very, very bad tool for these cases is that it is very hard to predict on which of these two cases we will be. It is very hard to know because of the generative model's complexity, especially as we go to more advanced generative models like generative adversarial networks, that we know in which case we're going to be. We know, is it going to learn about this outlier or not? Are we going to be in the case where there is a privacy leak, or are we going to be in the case where we're going to get to wrong conclusions? And kind of the key takeaway is that, well, the promise is very much not fulfilled. Synthetic data at the end of the day is subject to the same limitations as traditional sanitization. We cannot create fine-grained that can be safely shared and be useful. And it introduces a lot of noise on aggregate statistics. Really, guys, if you're interested in public aggregate statistics, just publish them. It's okay. You're not going to gain much for going through all of this dance of creating a generative model and putting more noise when you generate a synthetic data set. And on top of that, we believe that synthetic data has a drawback with respect to sanitization, which is that we lose interpretability. When we sanitize, we know exactly what we remove, we know exactly what we generalize, and we know what we're doing on the data. We're conscious. When we do synthetic data, we lose all of this capability, and we really don't know which parts of the signal have been preserved and which not, and we really don't know, well, which errors are we actually committing, because it is impossible to interpret what the algorithms do. And this is all that I wanted to say. I'll be more than happy to get questions.
Thank you, Carmela. We have some time for questions. If there are questions from the audience, please type them in the chat and we'll ask them aloud. I can start. I thought the presentation was nice in exploring a few examples of this anonymization process. But can you comment, are there any more generalized, let's say kind of a battery of machine learning tasks to see where is performance most affected? Are there some machine learning tasks where it doesn't matter or it matters more?
So we didn't do that study in depth, but actually some other people have done these studies about the utility. I have to say that the results I have seen are not very promising. And I think the problem comes in particular with this unpredictability of what is going to be preserved, right? It's very hard to say it's going to be good for this and not for that, because you don't really know what the synthetic data is going to have on the other side. So I'm sorry, and I'm sorry also, Filippo, I see your question that is kind of somewhat depressed, but we really have not found an answer to those questions to say it could be useful for this particular case, or it could be useful to remove some biases. It is hard. We don't even know if this amplifies biases or actually reduces biases. And in a way, it essentially does, well, what is expected when you put differential privacy, that is actually removing the outliers. And then you would actually, if you use this kind of data, you would be augmenting the bias, because you would not be counting anymore with these minorities, right? The kind of presentation we had before. So I'm afraid that I don't have a good answer for that. And that so far the works I have seen are not very hopeful.
I have a somewhat related question, which is, have you thought about, are there some important differences for this anonymization process when looking specifically at more causal inference type problems rather than machine learning problems? And I had in mind the idea of using healthcare data to get at the causal effect of some treatment, like a treatment choice on an individual based on their characteristics. It seems like doing some shuffling of the characteristics could be a bigger problem there.
So what I can say there, I haven't seen exactly any causal inference, but I have seen, for instance, people trying to use synthetic data for time series, just try to see how patients evolve over time, right? And then I have seen patients that when they were doing this thing, they were changing height over the course of time, because synthetic data did not actually model the correlation between the correlation between height and other attributes that were the thing that were kind of interesting. And as a result, when you were creating synthetic data models, it didn't actually catch with the idea that height in humans does not change over time. I mean, once you're an adult, right? Or changes very little. Some of us become smaller. So my expectation would be that no, you're gonna even have a further problem there, because again, like, you don't know which of the correlations will actually be picked by the generative model. So it is very hard to know where causality is going to be preserved or not, or where you're actually going to have the negative effect that some causality has appeared that was not in the raw data. And Filippo has a question in the chat. One of the main problems on anonymization is that advanced in computation techniques, new finding of all data, things we thought were anonymous become identifiable. Do we have any certainty that these synthetic data sets will be private, not only now, but in the future as well? No, absolutely. I mean, again, if you have differential privacy, then you will get that warranty, because it's the warranty of differential privacy, right? That once you output the data, there is no processing that you can do with this data that will allow you to go back and do the inferences about individuals. But when you get that warranty in privacy, what we show is that then you get this drop in utility, remove the outliers, and you get heavy noise. So the question here is that there's no real good trade-off. And it seems that in terms of trade-offs, in general, sanitization actually kind of works better. And I would say, and this is my personal opinion, nothing technical, that in many ways, sanitization is more honest in this question that you're asking, Filippo, about what about the future? Well, we know that sanitization does not stand the future. But if we go ahead with synthetic data, where we don't really understand how it is going and everything hints the other way around, we may actually wrongly believe that we have a long-term protection when we don't. But in general, what I would say is that if you have a long-term protection, it meant that you actually lost the utility of the data. So two connected questions. We're currently applying differential privacy protocols in real-world data sets that can have major consequences, like the census in the US. Do you think we're jumping the gun then? And what would be the solution? Limited access to previously vetted researchers. I think, jumping the gun, that's saying maybe too much, but I think that the consequences of the use of differential data and how it actually hides outliers. There have been many minorities in the US that have tried to raise their voice, but being minorities, it's hard to raise your voice, right? About the fact that it is a known thing that differential private protocols will erase them. And therefore that would create down the line problems on how we do allocation of resources, which is one of the main uses of the US Census. So I think that this use is very worrying. I'm very happy to see privacy technologies deployed in the field, but I'm scared about the implications that this may have, where we actually may not even start grasping the consequences. And what could be the solution? Limited access to previously vetted researchers. I think that, yes, that is the case. We don't have a way of publishing fine-grained data in a way that conserves all the whole utility. As I said, no fine-grained data can be safely shared, but that does not mean that we should stop science and we should maybe stop doing this thing. But yeah, maybe the control has to come in some other way. I don't see much like when I call this presentation anonymization of Groundhog Day is because this is the whole cycle we did for anonymization, right? Using technologies, more things, until Vitaly Shmatikov and Arvind Narayanan came out and said, like, guys, stop doing this thing. There's no way you're going to remove all of the information from here. And I see us doing the same thing again, like in a loop, like Bill Murray waking up.
Okay, in that case, I think that we can wrap up this session. Thank you, Carmela, for the exciting presentation and for everyone in the audience for the interesting Q&A. And thanks for all the presenters of this research spotlight session so far.